Welcome to The Explainer. Today, we're tackling a piece of medical magic, the MRI. We're going to find out how this amazing machine creates these incredibly detailed pictures of our insides. And here's the kicker. It does it all with giant magnets, not radiation. So how on earth do you create a perfect map of the human brain with just a magnet and the water that's already in our cells? Well, let's dive right in. The answer is this mind-blowing feat of physics, where our own bodies become the source of the picture. But to really get what an MRI does, we first have to talk about what it doesn't do.
All right, this is probably the most important thing to get. An MRI is a completely different beast compared to an X-ray or a CT scan. The big difference? It uses zero, and I mean zero, ionizing radiation. Instead, it's all about super strong magnetic fields and radio waves. And that one distinction, it changes everything, from how safe it is to the absolutely insane level of detail you're about to see.
So what is this thing really? Well, at its core, an MRI scanner is basically a giant, super chilled magnet. Its job is to map out the location of molecules in your body, and it's particularly interested in the ones in water and fat. And since, our bodies are mostly water, that makes the MRI an absolute rock star at seeing our soft tissues. And really, that's its superpower. An X-ray? Fantastic for looking at bones, no doubt. But an MRI, oh man, it gives us this view of our soft tissues that's just on another level. I'm talking about the crazy complex structures of the brain, or those tiny subtle differences in muscle fibers, or even the health of our organs. This is where the MRI really truly shines. It gives doctors a window into the body they just couldn't get any other way. So how does it do it? How does this machine make a picture out of forces you can't even see? It feels like magic, right? But it's pure, unadulterated physics. The whole thing works by messing with the tiny magnetic properties of the atoms that are already inside you. It's like this perfectly choreographed dance at the molecular level. And guess what? You're the dance floor. Okay, so here's the play-by-play. Step 1. That huge magnet gets all the hydrogen atoms in your body's water molecules to line up, all pointing in the same direction. Then, bam! Step 2. A quick pulse of radio waves comes in and knocks them all out of alignment. Step 3 is when the pulse turns off, and all those little atoms start to relax back to where they were. As they do that, and this is the cool part, Step 4, they release this super faint signal. And finally, Step 5, the MRI's special receiver coils pick up those signals and use them to build a picture. This is a great way to think about it. Imagine all those hydrogen atoms in your body are like trillions of tiny microscopic compass needles. The MRI first makes them all point north. Then it just gently taps them with a radio wave and watches how they wobble back into place. See, the machine isn't really creating anything. It's just listening for the echo coming from these little atomic compasses. The scanner is just a really sensitive antenna, perfectly tuned to hear that tiny wobble. Oh, and you know what I'm talking about, the noise. That loud, repetitive banging and clanging you hear during a scan. It sounds like the machine is about to fall apart, right? Well, it's not. That's actually the sound of these other, smaller magnets, called gradient coils, switching on and off at lightning speed, thousands of times a second. That rapid switching creates vibrations, which makes the noise. And it's not just for show. It's absolutely essential for figuring out the exact 3D location of every single signal coming from your body. Okay, so we know how the machine finds where the signals are. But here's where it gets really clever. It's not just about where the signal comes from, but also about how fast those atoms wobble back into place. Because you see, not all tissues let their atoms relax at the same speed. That's the secret sauce. An atom in fat is going to behave a little differently than an atom in water. By measuring that tiny difference in timing, the MRI can actually tell them apart and start building a useful picture. So radiologists can basically apply different filters to the image by changing the timing of those radio pulses. These are called weightings. For example, on what they call a T1 weighted image, fat looks bright and water looks dark. This is awesome for seeing the basic anatomy. But then you have a T2 weighted image where both fat and water look bright. So you might be asking, why would you want that? Well, here's why that's so useful. A whole lot of problems in the body. We're talking tumors, inflammation, infections, you name it. They all tend to involve extra water. So on that T2 weighted scan, these problem areas just light up. They stand out like a bright beacon against all the healthy tissue around them. And that contrast, right there, is how doctors can spot abnormalities. It's the core principle that makes MRI such a ridiculously powerful tool for diagnosis. And the uses for this are just huge, especially when we're talking about the brain. For neuroimaging, MRI is the absolute gold standard. It lets doctors see the brain's super complex structures with a clarity you just can't get anywhere else. It's essential for diagnosing everything from MS and dementia to finding the source of epilepsy or checking for tumors. And it's not just about what's going on in our heads. MRI gives doctors this incredible roadmap of the entire body. You can use it to check out a torn ligament in an athlete's knee, see exactly how the heart is pumping, stage different kinds of cancer, or spot lesions in organs like the liver. It's an all-around amazing tool. Okay, so it's clearly a powerful tool, but is it dangerous? And that's a really common question, a fair question. I mean, you've got this huge, imposing machine making all that noise, so yeah, let's talk about safety, because it is absolutely the #1 priority. The single biggest risk factor has nothing to do with radiation, but with the magnet itself. That thing is unbelievably powerful, and here's the key thing to remember. It is always on, 24/7. That's why the screening process for metal is so strict. We're talking no loose metal objects in the room, period. Because anything magnetic can turn into a dangerous projectile. And of course, with the scanner being so loud, hearing protection is an absolute must.
Now, some people do find the enclosed space a bit challenging, claustrophobic, and that's totally understandable. Modern scanners have things like open MRI designs and faster scan times to help with that. But here's the bottom line. While the experience can be a little intense, the procedure itself is fundamentally very safe. And that brings us back to its single greatest advantage, no ionizing radiation. That makes it a fantastic and, importantly, a repeatable option for diagnosis, which is especially important for younger patients.
So, there you have it. MRI gives us this absolutely unprecedented window into the living, breathing human body. It's incredible. But with this amazing power to see so much, you have to ask, how do we balance all this medical discovery with the potential risk of overdiagnosis, finding things that might not have caused a problem? It's a huge question, and it's right at the forefront of modern medicine. It really just highlights the incredible responsibility that comes with having technology this advanced.